Well, time certainly is flying by as we approach our 2-week mark before the exam, and we just put the finishing touch on our series, and we covered all that from start to finish. We're going to jump into some polars. It's going to take us approximately 3, maybe 4 nights to get through all of our polars, then we'll hit some parametrics, and that'll be it for the year. Polar basics here really quick, going back to your pre-calc experience. We're going to say that the y-coordinate rectangularly is always equal to r times the sine of theta. We know that the x-coordinate in a rectangular system is equivalent to r times the cosine of theta. We also know that x squared plus y squared equals r squared, where you're just visualizing a right triangle. Maybe that's the point plotted in a polar, and you've got your x, you've got your y, and here's the length of r. Now also off that same diagram, if this is your theta down here in that corner, we could say, and there's 2 ways to write this, we could say that the tangent of theta equals y divided by x, or we could say theta is the inverse tangent of y divided by x. It's a little arctan or inverse tan up there. So those are your big basics. Now as far as the calculus part goes, we're going to spend a lot of time focusing on getting comfortable with the graphs, plotting points, being able to graph them and visualize them. And what that's going to do, once we master the graphing, there's 3 things in calculus that we really need to know how to do. We need to be comfortable finding the slope at a particular point. We need to be comfortable finding the area of a curve or partial curve. And then we need to be comfortable finding the arc length of the entire curve or just a portion of it, like a petal again. So those are the 3 big calculus ideas we have to master. Real quick, we're going to practice converting some rectangular equations into polar. We're going to just keep things really simple here. With the first example, 1632 we'll call it. We notice that x squared plus y squared is really equivalent to r squared equals 4, or we could just say r equals 2. And what that turns out to be is just a circle that's centered around the origin with a radius of 2. 1633, y equals 1, we're going to substitute r sine of theta in for your y. If you wanted to solve for r, you could say r is equal to cosecant of theta. 1634, let's see, for the x, I'm going to put in r cosine. For the y, I'm going to put in r sine, and that's supposed to be equal to 2. So we could say something like r squared, and then instead of you could say just cosine times sine, and there's no reason you wouldn't say that, but I was kind of picturing almost a double angle in there, and so I'm going to say maybe 1/2 sine of 2 theta equals 2, something like that. Maybe multiply the half over and get a 4 over here, something like that. Let's see, 1635, I could say r squared sine squared on the left equals 4 times r cosine. Again, if you feel comfortable with the big 4 rules from pre-calc, you're going to dominate this particular mini topic. For x equals 1, I'm just going to say r cosine of theta equals 1, which then means r equals secant of theta. And then for 1637, a little more creative, I got r squared on the left, and then I could say e raised to the 2 times theta up there. Perhaps my favorite part about polars is the way that you can use multiple representations for the same specific point. And I want to throw out the point 3 comma 5 pi over 6. So let's just practice plotting that one. What I'm going to do is I'm going to extend to the right 3 units on the x-axis, which is going to put me right around here. And then what I'm going to do is I'm going to rotate counterclockwise 150 degrees or 5 pi over 6 radians, and that's going to put me smack dab right there. So let's see, we're going to put a big fat point right there. Okay, so that's our initial point. Now my challenge to you is to come up with 3 other representations of that point with either a different r value or a different theta or a combination of the 2. So let's see, I'm going to start with blue. And my first thought here is instead of, let's see here, I'm going to rotate all the way around till you see the 11 pi over 6, and then once I hit the 11 pi over 6, I'm going to shoot in the negative direction. So that particular one, I'm thinking, let's see, negative 3 comma 11 pi over 6. Another one would be, instead of going counterclockwise, I might just do a little bit quicker here. I'm going to go clockwise. This would be negative pi over 6 as far as a rotation, and then the negative 3. So that would be negative 3 and a negative pi over 6. And then last but not least, I'm thinking maybe we could do this. Maybe we could rotate let's see, this would be 7 pi over 6 radians if I went in this direction, and then I would just keep the R value at a positive 3. So how would I write that? I would just keep it positive 3, and I would say negative 7 pi over 6 if I rotated in the clockwise direction. So all 4 of those ordered pairs represent the same point right there. So our next point, we're going to kind of play the same game. I'm going to go extend 2 units to the right on the x-axis, and I'm going to rotate counterclockwise 7 pi over 4. Let's see, that'll put me right about there. Let's see if I can line that puppy up. Right there, smack dab there. Okay, so one of the things I'll be looking for in your notebook, let's come up with 3 other representations of that point by either negating the R, negating some kind of angle, or a combination of the two. Okay, we're going to touch on our graphing really quick, and we're going to talk about R equals 1 minus 2 sine of theta. And hopefully the rust is slowly coming off here with regards to polars, and you recognize that as a limacon with an inner loop because the B value right here is bigger than the A value, and that's what makes it a limacon with an inner loop. If the A and the B were equal, then it would be a limacon with just a sharp little dimple at the origin. And vice versa. If A was bigger than B, then it would be, let's see. Whoop, I'm sorry, I think I said that backwards. If A is equal to B, we can make a little note here. If A is equal to B, then it's a cardioid with that very sharp point at the pole. And then if A is greater than B, then we've got a limacon with kind of the real soft, smooth dimple that's rounded and differentiable throughout. But anyway, so how do we graph this rectangularly? What we're going to do is we're going to pretend that it says y equals 1 minus 2 sine of x. We've got our traditional y-axis here, and we've got our x-axis right here, and I'm going to say every 3 units, that's pi over 2 and pi, and 3 pi over 2 and 2 pi. Okay, now the first thing I do is, because I've got a vertical shift up 1 unit, I'm going to say that every 2 boxes is 1 unit. So right here is 1 on the y-axis. That's my vertical shift. So just to recap, I'm thinking y equals 1 minus 2 sine of x, and we're going to attempt to graph that. And let's see, I'm going to start right here, and then what happens is I'm going to drop down 2 units, and that's going to put me right here. And then I'm back to the axis, and then I'm going to go 2 units above, and I'm going to go right back to the axis. So this is what it looks like rectangularly, and we're going to try to match this up on the polar graph and draw the corresponding points. Now I'm going to call this rascal right here point A. Rectangularly, that's, let's see, 0, 1. Now remember how these match up. The theta matches up with x, and then the R value corresponds to the y value over here, and vice versa. So let's see. Rectangularly speaking, I've got a theta of 0 and an R value of 1, which is going to put me right there, and that is my point A. Okay, next one here. Let's see if I can change colors. Let's call this guy B. Rectangularly speaking, that's pi over 2, negative 1. So I'm going to go 1 unit to the left and then rotate pi over 2 units. That would put me right here. Or you could do the opposite, rotate pi over 2 first and then go backwards 1. I'm going to call that my B value. Let's see, this rascal right here, we'll call that C. That's pi, 1. And that's going to put me right there. And let's see, the real big rascal here, point D, that's 3 pi over 2, 3. That's going to put me right there. We'll call that, let's see, I forgot to put that's C, and then this one's D. And then the last one overlaps with point A, it would be right there. So the path that we took to get there, and I think the sequence in which we hit those points is just as important as plotting them themselves. And so what the last thing that we'll make a big deal out of is, let's see, these roots right here, which hopefully you recognize as pi over 6. Wow, that one's, I gotta change that color, eh? That's not a good color at all. Let's call this pi over 6, and then 5 pi over 6. Those correspond to the moments where you hit the pole. The first time you started here at point A, and when you hit the pole first, right there, bang, that's pi over 6. You then started the loop, you finish the loop, and the moment you finish the loop, that's 5 pi over 6, and that's when you exit that inner loop. The next polar curve I want to try to draw is R equals 2 times the sine of 2 theta. Now what you'll hopefully recognize here is that we're dealing with a rose, and if this value right there is even, this one right here, the 2 there, if that number is even, then we're going to have twice that number of petals. So once you see the 2 doubling the theta, then we know we're going to have 4 petals when we're all done. How do we graph y equals 2 sine of 2x rectangularly? Well, we've got an amplitude of 2, which affects the height, but more importantly, the frequency is 2. So we're going to see a total of 2 cycles between 0 and 2 pi, which means by the time I get right here to pi, I'm going to finish my first cycle. And my sine curve is going to start here. At pi over 4, it's going to hit a max. I got a root at pi over 2. At 3 pi over 4, we're going to have a min, and then at pi, we've got our next root. And so it's going to look roughly like this. That's not too bad. I'm going to be honest. That's one of the best ones I've ever drawn. Might have to save this one. So right there's your pi over 4, and right here is your 3 pi over 4. So let's try to correspond just these points before we go too much further. We'll call this point A, and it's 0, 0. So we're starting right at the pole, right off the bat. This is my next special point, B. That's pi over 4, comma 2. So I'm going to rotate pi over 4 and then extend out 2 units from the pole. And then right here at pi over 2, I am back at the pole. So here's what happens. I started at the pole, I looped out to pi over 4, and I came right back. So what you're staring at right now on my polar curve right now is 0 to pi over 4 to pi over 2. So if they ever ask you for the area of just one petal, the integral would go from 0 to pi over 2. Now, we're not content with just that. We're going to continue to graph some more. So let's call this point D, 3 pi over 4, comma negative 2. Let's see, 3 pi over 4, but negative 2. Ooh, that's going to throw me right back here. And let's call this point E. Point E is back at the pole. So I'm going to loop, hit that there, and E's right back where we started. So again, they're symmetric. They should be the same size. My green one's a little fatter than the red one I drew earlier. Now, if we continue to do the rectangular curve, at 5 pi over 4, we've got a max. So I go up there, 5 pi over 4, come back, and then at 7 pi over 4, right here, we've got a min. So swoop down, hit that, come on back. Let's see if I can find one more interesting color here to use. Yeah, that's probably the best I'm going to do. All right, let's call this F. If I wanted to plot F, that would be right here. So we come through, we hit the pole and back, and then my last one right here, we'll call this G. That's going to put me in the second quadrant. I'm going to loop, hit this one, and come on back. So we see a grand total of 4 petals, and I hope that you can appreciate how these points, A, B, C, D, E, F, G, correspond to the specific polar points over here. Alright, we're going to see how quickly we can buzz through this list. We want to identify each of the following functions as either a line, a circle, a cardioid, a limacon, or a luminescent. Now, when you see a luminescent, we haven't really talked about that in class at all. It is on your bear stack, though, and basically it's a crazy 8, and we'll talk a little bit about that. It kind of looks like the infinity symbol. And then also the rows. If the equation happens to be a limacon, we're going to specify whether it has an inner loop or not, and then if it's a rose, we're going to make an indication of how many petals there were. So the first one we've got here, I'm going to say because the 3 is bigger than the 2, it's a limacon, and it does not have an inner loop. It's the first picture we have up here on the left. It's just kind of got a soft roll to it where it kind of dimples back in towards the pole without touching it and then rolls back out. But it's very soft and smooth and differentiable throughout. Let's see. Going down that column, we've got a rose, and it would have a grand total of 6 petals. Oh, I lied. 3 is an odd number last time I checked, so it should be just 3. Hopefully you guys were screaming at that one. Let's see, the next one underneath that is going to be a cardioid, and the reason I know that is because the coefficients 1 and 1 are equal to each other. No, 16, 13, I want you to square both sides. I want you to say to yourself, r squared equals 9 sine of 2 theta. That right there makes it a crazy 8, or the luminescent. I think we saw a luminescent over one of the breaks, the assignments we had where we had to identify the topic, solve the question, and then do a what-if question. I thought we saw a real nasty polar with that luminescent. We had the bounds were 0 to pi over 4, I believe. Let's see. This next one, 16, 14, that's actually a line. If you move the secant over, you get r cosine equals 7, which basically means x equals 7, so you've got a vertical line right there. 16, 15, r equals 7 is just a very nice circle that's centered at the origin, and a radius of 7. 16, 16, the 5's much bigger than the 2, thus creating a limacon with a gigantic inner loop. Let's see, 10 cosine, that's just a circle. However, this one's not centered at the origin. What it's going to do is it's going to be symmetric with respect to the x-axis. It's actually going to have a diameter of 10 and a radius of 5. Let's see, 1618 is going to be a rose. And because 2 is an even number, we're going to have a grand total of 4 petals, very similar to the one we graphed just a moment ago. 1619, that's going to be a straight line. It's going to be diagonal. It is going to go through the pole. If I was graphing it, you can visualize pi over 3, 60 degrees. It would run right along that radial line in both the first and the third quadrant. Again, 1620, square both sides. You'll see the liminescent. And let's see, 1621 though, I wouldn't square both sides. I would just leave the radical 6 the way it is, and I would say we've got a rose with 3 petals. The radical 6 just affects the length of each petal. Let's see, 1622 is a circle. You know, hopefully you can buzz through these as faster than I'm going right now. If you didn't have to worry about describing them, you could hopefully go pretty quick. 1622 is not only a circle, but it's centered, symmetric with respect to the y-axis. It has a diameter of 5 and a radius of 2.5. 1623 is another circle, centered, or I should say, symmetric with respect to the x-axis. 1624 is again a circle, but this one is centered at the origin with a radius of 4. What do we got here? 1625. That's really a y. So if you think y equals 9, now we've got a horizontal line. 1626 is another line, but it's more diagonal. You can picture 30 degrees. It would run like this. And then the last one again is another liminescent, a crazy 8. And again, look in your bear stack for a nice visual image or a liminescent. Or you could grab your calculator, slap it in polar mode, and try graphing that one right there.